Hello everyone. We're excited to present our latest work on AI ML optimized higher order modulations with a neuromorphic receiver. This joint demo by Samsung, VIAVI and NVIDIA under the AI RAN Alliance will be showcased at VIAVI's booth at MWC 2025. Higher order modulations enhance spectral efficiency by transmitting more bits per symbol. However, in 5G NR, traditional square QAM modulations suffer from shaping losses of up to 1.53 dB relative to the Shannon capacity, especially as the modulation order increases. To address this, Samsung proposes AI ML-based optimization to develop new high-order constellations and bit-to-symbol mappings for improved reliability and performance. They developed non-uniform modulation constellations through offline training of the neural networks over AWGN channels. And these non-uniform constellations are used instead of the conventional QAM mappings. For 1024 QAM and beyond, training convergence becomes challenging due to the massive number of neural network parameters. To tackle this, we introduce 3 optimization techniques and specialized neural network architectures. One method constrains the constellation to a rectangular shape, while the other 2 leverage quadrant symmetry for better convergence. Once trained, these optimized constellation points can be stored and reused for future transmissions. Our ML optimized non-uniform constellations achieve over 1 dB shaping gain compared to conventional square QAM. This brings performance closer to the Shannon limit, surpassing even the state-of-the-art ATSC broadcast modulations. Practically, this translates to about 25% lower transmission power, improving efficiency across the network. AI-based receivers can replace multiple signal processing blocks, i.e., channel estimation, equalization, and symbol demapping with a single neural network. This improves accuracy in handling channel effects and hardware impairments. However, traditional artificial neural networks, or ANNs, or neural receivers provide performance gains at the cost of higher energy consumption. To overcome this, VIAVI introduces neuromorphic receivers based on spiking neural networks, or SNNs. Unlike standard ANNs, SNNs encode data using discrete 1-bit temporal spikes, mimicking biological neurons and leveraging the temporal dynamics to sustain information. Our proposed SNN-based neuromorphic receiver achieves significant error rate improvements over conventional 5G receivers. It also matches the performance of traditional NN-based receivers, but does so with 9 times lower energy consumption, making it a power-efficient alternative. In this demo, we showcase a downlink scenario where the base station transmits AI ML optimized higher order modulations and the user equipment employs a neuromorphic receiver to decode the 5G NR PDSCH signal. We harness the power of NVIDIA's high-performance GPUs to train our models efficiently, enabling faster convergence and optimal performance. This demonstration highlights AI's transformative potential in radio access networks, or RANs. By leveraging AI for non-uniform modulations and neuromorphic receivers, we enhance decoding performance and energy efficiency. Key goals for next-generation 6G networks. These achievements align with the AI for RAN Working Group's mission to develop AI-native RAN architectures, addressing critical performance metrics and accelerating the integration of AI into future wireless standards. This proof of concept showcases AI's pivotal role in scalable, energy-efficient 6G RAN systems. This testbed captures the set of hardware, software, automation, and infrastructure activities required to enable 6G-compatible research and development of new and evolving technologies for 6G networks. In the MWC demonstration, we will perform live testing on the VIAVI 6G testbed with a live GUI. We will generate PDSCH signals using the different QAM modulation schemes, apply an AWG or fading channel, and decode it at the user end. The GUI will show the verb performance of the different modulation schemes and receivers. The top block shows the system model. The bottom block shows the live modulation schemes and bit error rates. We also capture the real-time neural activity in the neuromorphic receiver and evaluate the energy efficiency based on total flops using 1024 area modulation at a 4/5 coding rate. We train on TDL-A, C, and E channels and test on TDL-D channels for a user walking at 2 meters a second and an 800 nanosecond delay spread. We demonstrate 4 scenarios. The first scenario comprises a traditional 5G NR transmitter with squared QAM modulation and a 5G NR receiver with an LS-based channel estimator. The LS utilizes minimal energy consumption with reasonable performance. This will be used as the baseline. In the second scenario, we replace the squared QAM modulation with AI/ML optimized 1024 ARRI modulation designed with QSL constraint. The ML optimized modulations outperform the square QAMs for 1024 ARRI modulation with LDPC coding by at least 1 dB, saving energy by around 25%. The MMSE channel estimation improves performance but at a higher energy consumption cost. The third scenario comprises AI/ML optimized 1024 ARRI modulation with an ANN-based neural receiver that achieves performance close to the MMSE channel estimator while reducing the energy consumption, but remains much higher than LS. Now we replace the neural receiver with a neuromorphic receiver. As can be seen, the performance is comparable to the neural receiver, but with the benefit of energy reduction by around 9 times based on flops. Through this demo, the audience will discover how AI-driven modulations and neuromorphic receivers can revolutionize wireless networks. They'll gain insights into how AI enhances spectral efficiency, boosts decoding performance, and drastically reduces energy consumption. Key innovations shaping the future of 6G and beyond, aligning with the AI for RAN Working Group's mission to develop AI-native RAN architectures.